Well, one thing that I wanted to go over, because it was not done well, is the discussion of the Heisenberg uncertainty principle. All of you have heard this statement. I would imagine that not many of you understand the statement. It actually is difficult to understand, I think. But I'm going to try to explain it the best we can. So there's various ways or ways in which we can talk about it. We talked about it in terms of the particle in a box. Remember, we said if a particle is going back and forth in the box at momentum p, clearly it must change momentum when it hits the walls because it's changing direction. And we use the uncertainty principle to show that the amount by which the momentum changed was given by h bar, or h divided by the length L of the box. It was something of this order. I won't go into the exact details. But this was one example. There's another example, actually in Heisenberg's essays or lecture series that he gave at University of Chicago. This was one of 3 examples that he gave of his own uncertainty principle. And I think it's much clearer than the book. I think the book's explanation is crap, basically. I think it's really bad. And not that it uses a correct idea, but it just doesn't explain it. It's just opaque. So maybe this will be less opaque. We'll see. But I'm going to try to go through it and take a look anyway. Okay, so the basic idea in all this is that imagine that we have a stream of particles that are described by some wavelength. So the dots represent the particle properties. The particles have momentum p. They have an associated de Broglie wavelength that's given by h divided by p. And as that wave goes through the slit, it diffracts. Right? We saw a couple examples earlier on, chapter 40 that we talked about, or 41. But we're going to now look at this as a single slit diffraction. So what happens when the particles go through the slit of width d? Well, they diffract. Right? In the process of diffraction, what it means is the particle directions change. Some of them bend upwards and some of them bend downwards. Some of them go straight ahead. And the intensity pattern on the wall looks something like this, I of theta. Right? And it's the same that we derive for waves. Only now we're looking at it from the particle point of view and saying, what happens when a particle goes through the slit? Then what is the probability that it lands at different points on the screen? And we said before that this is actually just equal to the number of particles times the single particle probability distribution p of y that we associate with the amplitude squared of the wave function, right? We did this just like we did for using the electric field. We did this and talked about this a few weeks ago. So this is a probability distribution, right? Sorry for the overuse of p. Little p is momentum, and of course we need to remember that. This should be, of course, little p. It's just that there's also a piece of y there, so I have to be careful how I do that. But p is equal to mass times momentum. And you worked a homework problem with this, with neutrons going through the channel between 2 rows of atoms. And you've already worked a couple calculations like this, right? So in the process of diffraction, what it means is that once the particle gets through the hole, through the slit, there's an uncertainty in what direction it goes. It may go above the x-axis, or by the way, speaking of axes, this is be the y-axis, this will be the x-axis, right? Some of them may go in the positive, and some are negative, and some straight ahead. So there's an uncertainty in the momentum, the y component of momentum. There's an uncertainty in py after it goes through the slit. In the words of Einstein, when the particle goes through the slit, God rolls the dice, decides whether the particle goes up, straight ahead, or down. Depending on the roll of the dice, the particle chooses the direction. We can no longer predict exactly where it's going to go. Remember, this is exactly the opposite of classical view, that if I know what the position and the velocity of a particle is, and I know what the force is acting on it, I can precisely find what the trajectory is, right? That's classical physics. This is violating classical physics. It says once the particle goes through the slit, even though there's no force on it, it still comes out at an angle that is with respect to the incident axis. If it was just acting like particles, then basically all the particles would uniformly go straight through. You get a shadow. You'd get intensity between here and here, and nothing outside of that. That's what a particle would do. It would simply either go through or it gets stopped. It goes straight or it gets blocked. So the intensity would just be between here and here, and it would be very narrow. But in fact, the intensity pattern looks like a wave. Right? So now we're trying to reinterpret what it means for a particle to act like a wave. Okay. So what it means is that because of diffraction, there's going to be an uncertainty in the y component of momentum. Right? How large is that uncertainty? Right? Well, I can calculate that because let's first of all decide how well do we know the position of the particle as when it exits the slit. Well, I'm going to write down that if I were to write down what I know about the coordinate of the particle, it would be y equals 0 plus or minus d over 2. Why d over 2? Because I only know that it went through the slit. The width of the slit is d. I don't know where it went within that slit, so it came through to the best I can ascribe a value. It has y equals 0. All I can say is it came through the center of the slit plus or minus d over 2. Right? That's the average value and the error. Similarly, I can do the same thing for p sub y. P sub y is going to be equal to 0. Most of them go straight ahead. If they go straight ahead, there's no y component of momentum. They're going to land right here. And that is, in fact, the average value. But there's plus or minus an uncertainty delta p. And I'm going to call this delta py max. So there's a maximum uncertainty. Okay? And I want to calculate what is this uncertainty in the momentum p sub y. Well, I can get that from the following. Let's suppose, which is also largely true, that 90% of the particles fall between the first two maxima. In other words, 90% of the particles have a sine theta, which is less than or equal to lambda over d, and they're greater than or equal to minus lambda over d. And this is true for 90% of particles. Let's suppose that I just want to average that and say, let's call this the maximum. Let's call this the maximum error because there's only a few percent, 5% to this side and 5 to the other, that actually have values larger than that. But most of them are going to have values of p sine theta, or I'll say p sine theta 1. So let's write it this way, that the uncertainty in the y component of momentum is equal to the maximum value that the y component can have, which is p sine theta 1, where sine theta 1 is equal to lambda divided by d. Okay? So this is the value that I have for sine theta 1. That's this value right here. Right? So the uncertainty in the y component can be written as p sine theta 1, where sine theta 1 is equal to lambda over d. Okay? This is all from the classical theory that we did back in chapter 2, or chapter 35, I'm sorry. Okay, so sine theta 1 is lambda. What is p equal to? P is equal to h over lambda. Right? So p sine theta 1, since this is the value, the maximum value I get for sine theta 1, this is the maximum value, therefore it's the maximum of p sub y. So this is equal to p is h over lambda, and sine theta 1 is lambda over d, and therefore this is equal to h over d. Okay? So the maximum that the uncertainty in the y component of the momentum can be is h over d. Right? What is the uncertainty in what is the uncertainty? This is the uncertainty in the y coordinate or position of the particle, delta y. So delta y I can write as d over 2. Right? So what is the product of delta y and delta p sub y? Well, this says then that if I take, which way? Delta y, and this will be a maximum error, right? We'll call this the maximum error, times the uncertainty in delta p sub y, which is the maximum uncertainty in the y component of momentum, right? Is going to be equal to d over 2 times h over d, and that's equal to h over 2. Okay? So the uncertainty of the product of the uncertainty in the y coordinate times the y component of momentum is equal to h over 2. That means to say that if I make delta y smaller and smaller, then delta p gets bigger and bigger. Right? The product of these two can never be less than this number. That is the Heisenberg uncertainty principle. Now, because we normally deal with RMS errors instead of maximum errors, turns out that if I were to do this in terms of RMS errors, I get the delta y RMS times delta p sub y RMS is equal to h over 2 pi. Okay? So it's actually small, all right? Because RMS errors are smaller than maximum errors. Right? RMS is a standard deviation. Maximum could be 3 standard deviations. So we definitely have that this number is going to be this product is going to be smaller than this product. Nevertheless, it is clearly or strictly a function of diffraction. The smaller I make delta y, the more accurately I know the position of the particle because it did go through a hole of a certain width, then the more uncertain is the y component because this whole distribution spreads out. The minimum spreads out and goes to a larger value as d gets smaller. Okay? So d gets smaller, therefore the uncertainty in the y component. Now it turns out to be generally true for all particles described by waves. So we're just giving you one example here. And there are other examples we could do, but it would take 4 or 5 hours probably to go through those. We're just trying to give you what I would call a brief introduction. Now, where does the inequality come from? The inequality comes from the fact that notice that I have put in a value of the uncertainty in y here, well, in terms of maximum is d over 2, right? That is true if I am measuring the position of the particle at the slit. But as soon as I go out to, let's say, a different distance, the rays are diverging. And that means that the uncertainty in the position gets larger. Okay? Because I've already given it a what do you call it, a random angle. You know, God rolled the dice and, you know, threw out a value of theta for that particle. And that theta now causes a divergence. And I don't know what that value is until I measure it on the screen. Okay? You know, the diffraction has occurred. The uncertainty has occurred. Therefore, I don't really know what the angle is until I measure it at a more distant point. As a result, the uncertainty in the position is going to be this envelope. It's going to get bigger and bigger as I go further and further. Right? So in general, the uncertainty at any other distance from the screen, delta y max, is going to be greater than or equal to d over 2. Okay? So in other words, this is only true when I'm measuring at the slit. If I measure delta y any place further away from the slit, then the uncertainty in the position grows because it's now been given a random angle of which I know nothing about because it diffracted like a wave. So there's that uncertainty in angle now means that there's an uncertainty in where it was. As I go further away, the uncertainty in position gets larger and larger because I don't know where the particle went which angle the track that the particle took. Okay? So that means at any later time, delta y is greater than d over 2. So I get the inequality that delta y max times delta p sub y max is greater than or equal to h bar. Or, I'm sorry, h over 2, since I'm doing maximum, is greater than or equal to h over 2. Okay? This is the Heisenberg uncertainty principle, right? That the product of the uncertainty in the position of a particle times the uncertainty in the momentum can never be smaller than this quantity. But since we're dealing with RMSs, it's actually h bar. Okay? People follow that argument? It is the wave property of the particle that leads to its uncertainty. Because it diffracts. And once it diffracts, I don't know what direction it went. And neither can I possibly know what direction it went until I make a measurement. But until I make a measurement, all I can say is, this is the product of the uncertainty in position and momentum. Everyone understand that? There's a randomization. This acts like a wave, but then I go, oh, but wait a second, it's not a wave. There's really a particle went through. Okay, the particle has a certain y component of momentum. What is it? I don't know. I just know it's between these two limits. Okay. So the particle acting as a wave leads to the uncertainty principle. Okay. Now, you may never ever use this again in your career. It may actually be of zero value to you. But, you know, part of your education is getting a cultural background. Yeah. I mean, I didn't like having to take English in college. I wanted to take math and physics. Medical students don't like taking organic chemistry, and they don't need organic chemistry. You guys may not want to be nuclear physicists, but you have to take some nuclear physics. So it's the way that life is, right? And it's not because we're trying to make it as painful as we had it. It's really because there is a value to broadening your education out. Okay. So even if you never use it again. Okay, so we go to this thing makes, I see a very puzzled look up here. So it starts as a particle, it diffracts like a wave, and then I detect it as a particle again.
So that equation would tell you just the distribution of whatever distance you're working with? Is that
the
right?
distribution in your uncertainty, yeah. I mean, this distribution is my uncertainty, or if you want to use the maximum, is the uncertainty in the y coordinate. Right? I only know the y coordinate to the accuracy with which is defined by the size of the hole. Because I can assume that if a particle arrived here and the source was over here, it had to go through the hole, or the slit. So if the slit is limited in size d, then the uncertainty in its position must be d over 2. Charles is going, go on, keep going, keep going. Okay. Okay. It takes a while to absorb it. Hopefully you wrote this down. It's on tape. You'll now be able to play it back if you have any questions about it. But this is the Heisenberg uncertainty principle. Now, there's another one that we began talking about, which we were not going to derive, but we will simply state that the uncertainty in the energy of a particle times the amount of time over which I make that energy measurement, delta t, is greater than or equal to h bar also. This is the second version of the uncertainty principle that complements this version, which is delta y times delta p sub y is greater than or equal to h bar. Okay? They're kind of symmetrical. Okay? And we'll talk more about that one in the next problem. Okay? Students, for the rest of this lecture, we're going to go into a greater detail on the particle in a finite potential barrier. And I'm going to do this with a slightly different explanation than you will find in the book. And I think it illustrates the problem better than you'll find there. The first thing we're going to do is state the problem. So what I've drawn up here is a a graph of the potential function of a particle that's trapped in a what we call a square well potential. So the particle, which in this case is an electron or a proton, is bound between these two edges. The difference between this problem and the one in the last lecture is that we're working for the case in which the potential barrier, which of course this is because it goes from u equals 0 at the base, that's where the particle is trapped, up to an infinite potential on the edges of the box or the edges of the well. So what we had last time was the wave equation and the energy levels for a particle in an infinite potential well. So this time we're going to derive or show you how to derive or analyze the energy levels and the wave function for particles that are in a finite potential. So now this quantity u0 is finite. The potential is still 0 within the boundaries of the box, but I have taken a slightly different tack. In the problem that we worked in the last lecture, the origin of the coordinate system, remember this is the x-axis on the base here, and the vertical axis is the energy axis. This region right in here is u equals 0, but we went from the left edge of the box to the right edge of the box over a distance L. So L was the distance, and typically we measure these distances in nanometers, and that's partly because Planck's constant is so small, and the electron or the proton is trapped within these bounds. Okay? Now, in this problem, we wanted to analyze the solutions when we have a finite barrier, but because of the symmetry of the potential well, we're going to choose the origin to be in the middle of the well. So in the previous example, we had the well that was extending from x equals 0 to x equals L. In this example, we're extending it from x equals minus L to x equals plus L. Okay? So L has a little bit different meaning. Okay? The L here is actually half the width of the barrier as opposed to the full width. And U naught is finite instead of infinite. And we'll see that makes the problem much easier to solve. Furthermore, I'm dividing the solution to the equations into three separate regions. Region 1 is to the left of the box or the barrier of the well, the square well potential. Region 2 is the region inside the box where the potential is equal to 0. And this, of course, is the other side where the potential rises abruptly to some finite value u naught. Okay? Now, we're going to solve it in the three regions. It's easier to start with the middle region, region 2. So we will look for the wave equation that we want to solve. Well, the wave equation here is exactly the same as the wave equation or the Schrodinger equation for the case with infinite wells. The difference being, however, that the wave function does not vanish at the boundary, and we find that there are solutions that give you a finite probability function at regions that are beyond the edges of the well. Writing down the equation in the middle, we're going to have the same as last time. So there's no mystery here. So in region 2, so say in region 2, the Schrodinger equation is going to look like minus h bar squared over 2m times the second derivative with respect to x, psi 2, and of course this is a function of x, but I will leave that off right now. And this is equal to e times psi 2, right? And of course psi is meaning psi is a function of x, of course, right? Okay, so this is the Schrodinger equation in region 2, and it's going to have the same solution as last time, namely we can multiply through by minus 2m over h bar squared, bring the term on the right over to the left, and we get that the second derivative with respect to x squared of psi 2 plus 2me divided by h bar squared times psi 2 is equal to 0, right? And we did this last time. That's the same as the equation we had in the previous problem with the infinite barrier. But, so we can just write down the solutions right away. We get that psi 2 of x is equal to a linear combination of sine and cosine. So I'm going to write sine. And because we know that k, and by the way, k squared is this coefficient right here, so let me just write that down. K squared is equal to 2me. And since the energies are quantized, I'm going to put E sub n, and I'm going to divide this by h bar squared. Fine, okay. So I now am going to write the solution in terms of k or k sub n. Let me put the sub n on here. Sine k sub n, x plus b times cosine of k sub n x. So both the sine and the cosines are solutions to this differential equation. Therefore, any linear combination of these two will also be a solution of this differential equation. So that's as far as we had last time, but now we have something a little bit different in the region 1 and 3. Right? So let's look at the Schrodinger equation in regions 1 and 3. So in regions 1 and 3, then I now have a finite potential. So over here, I have to put in the potential function inside the Schrodinger equation, and that's minus h bar squared over 2m times the second derivative with respect of psi with respect to x plus u0 times psi is equal to e times psi. Now, one thing I want to make clear that we are looking for solutions which are called bound states, okay? So let me write this out. For a bound state, that is to say a particle whose wave function is captured within this region, and sort of like the particle that cannot get out of the box, we say that for the bound states, the potential energy height is greater than the energy E sub n of the particle. So if I were to draw, let's say, energy E1, E2, E3 all the way up, they all up below U0, otherwise they are not bound, right? And furthermore, within this region, within the central region, I should say, we can say that E sub n is equal to 1/2 mv squared, right? So in other words, the energy is the kinetic energy in the region where the potential is equal to 0. Okay, so we've got that written down. Now, the second part is that I want to solve this equation, so I'm going to subtract E times psi, and I'm going to multiply through by minus 2m over h bar squared, and I'm going to get a slightly different differential equation than we had before. Namely, it's going to be the second derivative of psi minus u0 minus e times 2m divided by h bar squared times psi is equal to 0. Now, remember, u0 is greater than e, so this quantity in here is positive, but I'm subtracting a positive, so the sign in front of here is minus a positive quantity coefficient, whereas over here it's plus a positive coefficient, right? And because of that, the solutions are slightly different. Namely, for those of you that have had some differential equations, this may be redundant or a little bit easier for you, but this whole quantity, this positive quantity in here, we call g squared. And if I do that then, I then get that the second derivative of psi minus g squared times psi equals 0. And there are two solutions to this equation. That one of them is e to the gx, and the other one is e to the minus gx. And those are independent quantities. I cannot express one as a multiple of the other. And the theory of differential equations says there are two independent functions that will satisfy a second order differential equation of the kind that we're looking at. So in that case then, we use the same principle that any linear combination of these two will also be a solution. So in this case, I'm using coefficients C and D, and this is my solution for regions 1, or it's psi in region 3. But the coefficients will be slightly different. Now notice that the shape of the wave function in region 1 and 3 must have the similar or exactly the same exponential shape to them. That's because by symmetry,
the forces on the left at this barrier of the wall are the same as the force here, and so by symmetry, whatever probability I have over in this region must be the same over in this region for finding the particle. Okay, now a couple things we have to do. First of all, we have to look at 1 and 3 separately, regions 1 and 3. So let's look at region 3 first. In region 3, what I see is that for region 3, I must have, for x greater than L, I must have C equals 0. And the reason for that is that if C is not equal to 0, then the wave function becomes infinite as x goes to infinity. And that means that the function psi cannot represent a probability. Therefore, in this case, it's equal to 0. Furthermore, in region 1, I can make the similar argument that in region 1, for x less than negative L, this should be a less than sign, I must have that d is equal to 0. So I can now write down what the wave function is for the two regions. So for the case of in the negative x region, I'm going to have this exponential. In the positive x region, I'm going to have this exponential. So I'm going to write them separately, right? And so what I'm going to do is say that psi 1 of x is equal to, this is in, in the negative region, must be equal to c times e to the gx. And in region 3, this will be d times e to the minus gx. Okay? Now, in order to make this a little simpler to analyze, I'm going to replace the constant c with another constant. It's going to be determined by boundary conditions anyway. So I'm going to replace c with c times e to the gl, and I'm going to replace d with d times e to the, I'm going to put a minus sign right here, then the plus sign is e to the gl, and then I'm going to, making this replacement, then I'm going to get that psi 1 of x can be written as, in the negative region, in the negative x region, c times e to the g x plus l, and in psi 3 of x is equal to d times e to the minus g times x minus L. Looks like the only mistake I made was these should both be positive exponents when I do the replacement. So, in other words, e to the GL is a constant. It doesn't depend on x. So I can redefine the constant to make it as simple as I want. And the reason I do this is that I want to have the condition that the evaluation of the exponential at the edge of the wall, which is at, in this case, psi 1 of minus L, is equal to c, and the wave function at the edge of the other wall, which is at plus L, is going to be equal to d. Okay, so I just redefined the constants so that it will make the math a little bit simpler going forward, and these are my two equations. Furthermore, and this is an important point, that due to the symmetry of the situation, the probability of it being in the left side of the barrier is equal to the probability of it being on the right side of the barrier, and probability goes as psi squared. So I must have that psi 1 of squared minus L. By the way, this is for x less than minus L. This is for x greater than plus L. Psi 1 squared of minus L is equal to c squared in this definition, and psi 3 squared of plus L is equal to d squared. And furthermore, these two must be equal to each other. Therefore, c squared is equal to d squared, or c is equal to plus or minus d. Okay? Those are the possibilities that I have. And because of the fact that the wave functions alternate, which we will find in the solution, but if we look at the case of the infinite square well, using the axis of symmetry as the middle of the well, calling this this point O prime on the x-axis, then the first wave function is symmetric, so it's an even function. If I choose the origin in the middle, right here, this one is an odd function, the next one will be even, and the next one will be odd. So the wave functions go from even, odd, even, odd, even, odd. Right? Using this, then what we see is that the way that we're going to incorporate that is that the even and odd, they're even if C equals D, and they're odd if C equals minus D. So we're going to incorporate that and choose the case of that C is equal to, or I should say D, let me check my notes here, that I'm going to choose my condition for whether the function is even or odd by saying that D is equal to minus 1 to the n plus 1 times C. So in other words, if n is equal to 1, this is an even function, and I get that because I know, at least for the infinite well, I get the half sine wave curve, and that is an even function. And in the limit that the finite well gets deeper and deeper, it resembles more and more the same shape as the infinite well. So this is a useful way for us to characterize this. Now the rest of the problem depends on depends on boundary conditions. So now we have to apply, as we did with the infinite well, with the boundary conditions. Boundary conditions. And the boundary conditions for the finite well potential are that, first of all, that I have that the wave function psi in region 1 evaluated at minus L must be equal to psi in region 2 evaluated at minus L. In other words, the wave function needs to be continuous across the boundary. That the wave function that we have, this is the wave function in region 2. The wave function in region 1, which I can also write down here as soon as I find my pen. But I've already got it right here. This is the wave function in region 1 and, of course, in region 3. So these are the three wave solutions to the differential equation. This is the solution within the square well. This is the solution to the left and to the right of the boundary of the well. So that's the solutions I have to deal with. Now the problem is, what are the constants? And particularly, in order to solve this problem, we need to know the energy, right? The energy. And Kn, the energy is defined through the wave number k sub n, where k sub n squared is 2me over h bar squared. So if I know what k sub n is, I know what the energy level is. So that's something I have to keep in mind. We will get to that very shortly. But first of all, we have to use these boundary conditions in order to get closer to determining the coefficients in this equation. So if psi in the region 1 of minus L is equal to psi in region 2 of minus L, then I write that down. We've already established that psi 1 at minus L is equal to the constant C, and the psi 2 in region negative L is going to be this function evaluated at minus L. So I get that this is equal to A times sine, assuming I did that right. Yeah, sine of minus KNL plus B times cosine of minus KNL. And also, because of the fact that the sine function is odd and the cosine function is even, I'm going to rewrite this by bringing the minus sign outside of the sine and cosine and replacing them with their respective values. And so I'm going to rewrite this with the cosine term first. This is B times cosine of KNL minus A times sine of minus KNL. Okay, that's the boundary condition at the left side of the box. Now, I also have a boundary condition on the right side of the box. So on the right side of the box, I'm going to have psi of 2 region 2 evaluated at plus L is equal to the wave function in region 3 evaluated also at plus L. So that will be my other boundary condition. Okay. Now, at plus L, on the right side of the box, I have, let's see, I'm sorry, yeah, the region 3 is on the right side of the box. I have this expression with the substitution that d is minus 1 to the n plus 1 times c times e to the minus gx. So notice I've just replaced d with the assumption that the wave function is either even or odd by minus 1 to the n plus 1 times c. So having done that, and if I do that, then I get that, I want to write this a little different. Let's call this region 3 and this one region 2, so I can get the equations written symmetrically. This is the boundary condition. So I get that on the coming from the in region 3, I have minus 1 to the n plus 1 times c equals b cosine of kn plus a sine kn. Okay? And so let's take a particular example that if n is odd, so if I say that n is for n odd, that means minus 1 to the power is just plus 1. Then for n odd, I get that c is equal to b cosine, and then on the other side, I just rewrite that stays the same, cosine kn plus a sine of, oh, but did I make a mistake here? Yes, this should have been plus, sorry. This is plus, there you go. I brought the negative sign out of the argument. Sine of a negative angle is minus the sine of the positive angle. And for the second term here, I have sine of k sub n times L. They are both equal to c, therefore they're equal to each other. And the only way this expression, which notice that they are identical parts in each on the right and left of the minus sign, the only way this expression can be equal to this expression is if a is equal to 0. Okay? So what that tells me then is that for n odd equals to an odd number, then I get that the wave function in the middle region, psi of x, is equal to b times cosine of KNL. And similarly, if I go through the same exercise with n even number, then what I will do is replace the c in this equation with a minus sign out front, and then comparing it to this equation by reversing the signs on these two terms. If c gets replaced with a minus c, then I will reach the conclusion that a is equal to 0, and therefore that psi 2 of x is equal to a times cosine of kn. Oh, by the way, this should be x, knx, right? So now I've simplified the original equation as the sum of a sine and cosine, and said that for individual solutions, depending on whether the nth energy state is even or odd, the answer is that for the wave function, that it will be one of these two cases. And this now is the new solution. While we are on this point of writing down the wave equation, which we have done for the central region, we can also write down the wave equation in region 1 and 3. So we can say then that for n odd, we get that psi 1 of x is equal to c times e to the gx. And in region, well, we'll come back to that in just a second. And in region 3, this is equal to c times minus 1 to the n plus 1. So if, we'll just write down n plus 1 times e to the minus gx. And by the way, I should say that these are generally true. This is for n even and n odd, and this is also true for n even and n odd. So our general then solution consists of these three or four equations, depending how you look at it, but I can write them down. But one of the points or features is that for any given set of value of n, there is only two variables to solve for, or three, I should say. There's b, c, and k sub n. Notice that g is also a function of k sub n, or energy. So remember that, and this is actually what we're after next, k sub n is equal to the square root of 2m e sub n over h bar, and g is equal to the square root of whatever we had over on this side, 2m u0 minus e divided by h bar, or e sub n. So the point is that we still have to solve for the energies e sub n, but we at least know what the wave functions look like in the three regions for n even and n odd. These are two different wave functions for psi 2, but there is only one wave function for regardless of whether n is even or odd. So these two are generally true for all cases. Okay. So the easiest thing to do is, if we think about the method forward, if we can solve for the energies, which is obviously what we want to do in quantum theory, we want to solve for the possible energy values E sub n for a square well potential. That is, after all, that is in fact what we're after, these quantities E sub n. So we're now in a position where we can do that, and I'm going to erase a little something on this side so that I can get a little bit more room. But the point is that once we have these energies, we know what G is, we know what K is. If we go back now to our wave functions, the only thing left to solve for is B and C, or A and C, right? So if I have an odd function, my unknown coefficients are B and C. If I have an even function, my unknown coefficients are A and C, but they will still be determinable after we solve for the energy. In other words, once we have the energy, we have values to put in for Kn, and we have values to put in for G. So getting the energies is the next step. How do we solve for the energies? Okay. Well, to solve for the energies, we need another boundary condition. So we're going to come up with a new boundary condition. New boundary condition, and that is the following. Previously, we used the fact that the wave function was continuous across the boundaries, right? Psi, the wave function in region 3 at L was equal to the wave function in region 2 at L, and they had to match each other. There is an additional boundary condition which says that the derivative of the wave function must also be continuous across the boundary. So we're going to have a new boundary condition that the derivative of psi 2, psi in region 2 of x, evaluated at x equals L, must be equal to the derivative of the wave function in region 3. I'll make sure I did this right. Yeah, region 3 with respect to x, evaluated at x equals L. That's a condition that not only does the wave function have to be continuous across the boundary, but the derivative has to be continuous across the boundary. And there are a couple reasons for that. One is that the Schrodinger equation is an equation that involves the second derivative. And the second derivative can only exist if the first derivative is continuous. If the first derivative is discontinuous, then the second derivative does not exist at the boundary. But furthermore, another important reason is that looking at the equation that we have up here, that if u0 is finite and e is finite, then the second derivative must also be finite. And the only way that can be finite is if the first derivative is continuous. So the new boundary condition is given by this scenario right here. So what we can do now, it's a very slick trick, and I'm going to show you how to do it. And there's a extra credit problem if you so choose to do it on Blackboard. And that is that someone was very clever with this and basically said, well, if this condition is true and this condition is true, then it must be also true that taking the derivative with respect to x divided by the function itself, it must also be continuous. So I'm going to put psi 2 evaluated at L, and over here I'm going to, oh, this should be division, I'm sorry. This is, yeah, that's 1 divided by, yeah. So this is a real division. Of course, this expression is a derivative. And then on this side, I'm going to also divide by the wave function in region 3 evaluated at x equals L. And so I get that 1 divided by psi sub 3 of x evaluated x equals L must be equal to the other side. So what it says is that the derivative evaluated x equals L divided by the function itself in the middle region must be equal to the derivative of the function evaluate x equals L in region 3 divided by the wave function at x equals L in region 3. So this is the equation that we use. It's actually clever. It incorporates 2 boundary conditions, both the derivative being continuous and the function itself being continuous, which is given from up here. The task that lies before you, should you so decide to do that, is that we have expressions for psi 2. Psi 2, whether depending on whether even or odd, if I take the case first for n even, then I'm going to start off with psi 2 of x equal to a cosine of k in x, right? This is on the side that you see here. And then I am going to look at region 3, and if n is even, then, oops, I made a mistake here. If n is odd in region 3, this should be the sine function. And hence, this should also be the sine function, right? And I'm going to use this function in region 2. In region 3, if I'm doing n even, then I want to be able to express the wave function in region 3. So the wave function in region 3 is going to be psi 3 of x is equal to, for n even, is going to be equal to minus c times e to the minus gx. So I have a wave function for psi 2. I have a wave function for psi 3. I have the boundary condition, which is this. And if I apply this equation to these 2 functions, then I can actually end up with a very nice result that gives me one of the first boundary conditions. And that is that we can write that the cotangent of the square root of 2m e sub n divided by h bar squared times L is equal to minus the square root of u0 minus en divided by en. And this is for n even. And there's a similar one for n odd, and that becomes the square root of, or I should say the tangent of the square root of 2m e sub n over h bar squared times L is equal to the square root of u0 minus en over en. So this is as far as we can take it analytically, but here's the point. We have a function that's either a cotangent function or a tangent function, and on the left, and on the right side, I have a sort of a 1 over e sub n behavior, right? So I can abbreviate this and call this the square root of u0 divided by en minus 1. And now I can plot for a given value of u0 here. I can plot this equation. This is my first function, which I call y1. This is my second equation, which I call y2. And I can plot these for this function as a function of e sub n. And the tangent function is going to be 0 at 0. So this is going to be a function that does something like this. And then at pi, so this is 0 to pi over 2. And then over here I will have pi. And I will get another tangent function that does something like this. And it will continue so that I get a tangent function that looks like this. These are my values, or my functions y1 in all 4 of the lines that I've drawn right here. So this would be pi, this would be equal to 2 pi, this crossing would be equal to 3 pi, if I've done this right, I hope I have, etc. So I have a sequence of tangent functions. On this side, I have a function which goes to 0 when En is equal to when En or E is equal to U0, and at very, very small values of E sub n or E, this thing becomes infinite, right? So the second curve, y2, does something that goes up like this. So y1 is the tangent curve, and what I'm looking for to solve for the energies is the intersection of these curves. And there will be multiple intersections up to a maximum value E, which is equal to U0, because E cannot go larger than E0, because otherwise this becomes imaginary. So these intersection points then give me the points of where or how to find the values of the function. I can't really explain it in much more detail, but I do have an example on Blackboard where these functions are plotted out, and you can solve for the intersections, and from that determine what the energy levels are. Okay, all right. So that is essentially what we have. One of the final steps we want to make in the discussion is, the final points is conservation of probability. So this is how we solve for the other variables, which are the coefficients. The coefficients B, A, it's B and C or A and C, right? We have two coefficients that we have to solve for, and of course they are related. They are related because from the boundary condition, which we had written somewhere up here earlier, the boundary condition said that C is equal to B times cosine of Kn times L, assuming if Kn is known, right? Then the B and C are related, and similarly there's a relationship between C and A. So before I write all that down, the conservation of probability says that the integral of the wave function squared, and I'll write this as amplitude squared, that the particle is found somewhere along the x-axis must be equal to 1. Right? That's a statement of conservation of probability. Now, in our case, we have wave functions in three different regions. But we can all agree that when we square the wave function, that the probability on the left of the box is going to be equal to the probability on the right of the box. So I'm going to simplify that and simply say that, that what I'm going to do is I'm going to take 2 times the integral from minus infinity to infinity of the wave function on the left side, so it's c squared, e to the 2gl times e to the 2gx dx plus the integral from minus L to plus L of a squared times sine squared of knx. Now remember, we're assuming we've already solved for the energies. So if energy is known, if E sub n is known, then Kn and G, or I should say G sub n, but we'll just leave it for G right now, G are also known, right? And we assume that's true. So we have actual values to put in here for Kn of x, because once we've been able to solve that, and we get that this function, sine squared kn dx is equal to 1. Now, this is the integral over regions 1 and 3, and this is the integral over region 2 for a particular case. Now, because it's a sine function, then I know that sine functions would be, this would be the case for n is equal to an even number. And of course, I would have a similar equation if it was an odd number. I would replace this with b squared times cosine squared of k and x. But either way, notice that when I do these integrals, there's only 2 unknowns. So the unknowns are a and c. And furthermore, we've just determined, and I hope I got the sign convention right here, that c is equal to b times cosine of kn times L. this number is this is a number, this is a number, cosine is a number, therefore I know that, I'm sorry, I was looking at C. Yeah, no, I was using the n odd function. So let me make sure I've got those numbers correct. Give me 1 second. Yeah, and this was B for n. This is for n odd. So yeah, this is n odd, and for n even, which is the case we're doing right now, we have from the boundary condition that C is equal to A times sine of Kn times L. Okay? So the point is that I have a substitute in here for C I can put over here, and now I only have one unknown, which is A. So once I have solved for A, I can go back here and solve for C, and then I'm done. So the route of the solution was we first use boundary conditions to determine the intersection of multiple curves given by these two functions that satisfy these two equations, which only have analytic solutions. Only have graphical solutions. And from this, I determine the energies E sub n. I also determine K sub n, right? In fact, I can express it in terms of K sub n. And therefore, I know with En, I then know what Kn and Gr are also known. And then, with conservation of probability, A is also known. And then that means, of course, that I also can find out what C is. If I know what A is, then C is known. So this is how you solve the problem using conservation of probability. And I think I will stop there. We'll stop there.